Simultaneous localization and mapping, referred to as SLAM, is the process by which a robot recursively estimates a map of its environment while simultaneously localizing itself against this map. At present, SLAM algorithms developed for unmanned ground and air vehicles in unstructured, real-world environments have demonstrated the ability to produce high-quality 3D maps with centimeter-level accuracy. As a real-world example, the figure shown to the right illustrates a 3D point cloud map produced by the commercially available Carta Stencil, which is a turnkey handheld sensor kit with integrated online SLAM. If a turnkey system can produce maps of such visual quality, what research in SLAM is left? SLAM approaches, developed for ground and aerial robots, typically fuse exteroceptive sensors, such as light detection and ranging, i.e. Lidar, and vision, proprioceptive sensors, such as inertial measurement units, i.e. IMUs, and positional sensors, i.e. GPS. In some combination, the most popular and effective formulations in past literature being Lidar Inertial SLAM, LIS, and Visual Inertial SLAM, VIS, for which there are many implementations. Note that GPS is often excluded from the formulation, as SLAM often operates in GPS-denied environments. Accuracy and robustness improvements have only recently been advanced by formulating SLAM around tightly coupled Lidar-Visual-Inertial odometry. This state-of-the-art framework unifies all three sensor modalities under one optimization problem for compensatory redundant state estimation. Works building upon tightly coupled Lidar-Visual-Inertial odometry are limited, though each had their separate motivation for extending this framework. In Again et al., the authors were motivated to exploit the localization potential of ultra-wideband sensing via additional relative position constraints, highlighting improvements that can be made in environments of high-strength telecommunications infrastructure. In Weiss et al., the authors were motivated by current limitations in deploying legged robots in extreme environments, such as those faced in the DARPA Sub-T Challenge. They demonstrate via a novel formulation of legged odometry for quadrupedal robots that degeneracies in exteroception can be recovered for greater accuracy and robustness. In a similar vein to Weiss et al., we are motivated by the current limitations in deploying unmanned surface vehicles, i.e. USVs, in degenerate environments, particularly those in which LiDAR and camera sensor fusion can be erroneous. Given the capacity of USVs to sense both above and below the surface of water, we maintain a tightly coupled Lidar-Visual-Inertial SLAM system for above water sensing while also fusing a Doppler velocity log for below water sensing. Doppler velocity logs, i.e. DVLs, are a type of acoustic sensor specific to marine robotics, providing high accuracy linear velocity measurements with newly affordable devices yielding 0.1% accuracy. With Again et al. And Weiss et al. Demonstrating accuracy and robustness improvements over their base tightly coupled Lidar-Visual-Inertial SLAM implementations with additional sensor fusion, we expect similar outcomes with DVL fusion. Within the greater context of robotics, our work has the potential to advance state-of-the-art SLAM for mobile robots, motivating other researchers to continue extending the tightly coupled Lidar-Visual-Inertial framework to suit their specific applications. Specific contributions made in this project are 1. A novel DVL factor based on pre-integrated linear velocity measurements from a DVL and angular velocity measurements from an IMU. Given that state-of-the-art, tightly coupled Lidar-Visual-Inertial SLAM is implemented as an optimization problem, factor graphs are used to graphically model conditional probability densities on variables of interest. In SLAM, these variables are typically robot pose and landmark features, with factors forming constraints on and/or between variables. In fusing pre-integrated measurements, our DVL factor acts as a binary odometry factor, constraining successive robot poses. Details of the complete DVL factor derivation will be provided in our final project paper, with our presentation discussing the mathematical framework. Secondly, we develop a method for reconciling DVL measurements with IMU measurements to effectively integrate DVL data at IMU rate. This provides the granularity necessary for the DVL factor to accurately pre-integrate DVL data while also handling asynchronous data capture between DVL and IMU sensors. Previous work integrating DVLs into USVs involves their coupling within inertial navigation systems, which have been composed of some combination of IMU, gyroscope, altimeter, and piezometer sensors. This body of work has employed various filtering methods, the most popular being extended Kalman filters. To our knowledge, the inclusion of DVL measurements within factor graph SLAM comes from the work of Lidar-Visual-Inertial, who formalized a DVL measurement model to propagate linear velocity measurements directly forward in time. This formalism neglects sensor bias, which accounts for the inherent drift in the mean measurements obtained from a sensor. By not optimizing for these bias terms, noise modeling is hindered.
For this project, we have chosen LVI-SAM, developed by Shan et al., as our base tightly coupled LVI-SLAM system. LVI-SAM tightly integrates the Lidar-Inertial system from LIO-SAM with the Visual Inertial system from VINS Mono. With this tight coupling, each subsystem may act independently when failure is detected, or jointly when enough features in both subsystems are present. Though other LVI-SLAM systems exist, LVI-SAM provides its implementation as an open source software, allowing our work to focus exclusively on integrating our DVL factor. Moreover, LVI-SAM is configurable to sensor calibrations, feature matching and thresholding, optimization tuning, and loop closure detection, yielding state-of-the-art results over previous LI and VI systems. The contributions of Visual Inertial Odometry, VIO, Lidar-Inertial Odometry, LIO, pre-integrated IMU odometry, and loop closure factors are jointly optimized in the factor graph presented here, with variable x sub I representing keyframe poses. A keyframe can be thought of as a regular intervaled snapshot in time, with LVI-SAM publishing keyframes at LiDAR rate. In brief summary of existing factors, LIO is derived from scan matching, where current LiDAR keyframes are matched to a global feature map. VIO is obtained by optimizing errors of visual reprojection and IMU measurements. Loop closure is the task of deciding whether or not a robot has returned to a previously visited area. Candidates for loop closure constraints are provided by the VIS and are then optimized via scan matching in the LIS. IMU pre-integration is the process of taking IMU measurements between two keyframes and summarizing them in a single compound measurement. This compound measurement constrains the motion between two consecutive keyframes and is formalized in the seminal work of Forrester et al. We finally arrive at our contribution for this project, which is the inclusion of our novel DVL factor. Our process for deriving this factor is templated on that of the IMU pre-integration. Here we illustrate the measurement models for both IMU, shown to the left, and DVL, shown to the right. IMUs record angular velocity and linear acceleration at high rate within their inertial frame. Measurements are contaminated with a slowly varying bias term, B, and zero mean Gaussian noise, eta. As for the DVL, only linear velocity measurements are obtained within the sensor's body, and are again contaminated by bias and noise terms. By leveraging angular velocity measurements from the IMU and transforming these measurements with the DVL's frame, we can reformulate the methods of Forrester et al. To integrate over linear velocities instead of linear accelerations, given that the same kinematics hold for both sensor types. By substituting linear acceleration for linear velocity, we arrive at the following compound measurements shown to the right for our DVL factor, with compound measurements shown to the left for IMU pre-integration for reference. We note that the relative change in rotation remains the same for our DVL factor, with its associated residual set to 0 to not double count the signal from IMU angular velocity measurements. For our DVL factor, no relative change in velocity is computed, as the single integration of linear velocity simply cannot produce a compound measurement, unlike the double integration of linear acceleration in the case of IMU pre-integration. Under the assumption of conditional independence and Gaussian noise, the factor graph optimization problem is that of least squares minimization, where x sub k contains the history of states x sub I for all keyframes I and the set of keyframes kappa sub k. In LVI-SAM, existing rotation, position, velocity, and IMU bias states remain, with the inclusion of the DVL velocity bias state, b to the v sub I, introduced by tight coupling of the DVL factor within the existing graph. With the inclusion of DVL residuals, for which complete derivations are provided in our final paper, the complete least squares minimization problem is also presented, where existing residual terms may be found in the paper by Shan et al.
To implement the discussed mathematical formalization for our DVL factor, we first develop a method of reconciling IMU and DVL measurements to obtain angular velocity and linear velocity measurements with 1, the same coordinate frame, and 2, a shared time point. Reconciliation is necessary for pre-integration to hold, with the method producing a pseudo-sensor measurement giving both angular velocity and linear velocity. Using extrinsic calibration, we transform DVL data from the DVL's coordinate frame into the coordinate frame of the LiDAR. Within LVI-SAM, IMU data is also transformed into the LiDAR frame, completing a fully connected link relating the rigid body translation and rotations between DVL and the IMU. With measurements aligned in space, measurements are then aligned in time using an interpolation scheme. Given high-rate IMU data, we maintain DVL pre-integration at IMU rate to leverage the granularity of angular velocity measurements. In doing so, the relative change of position estimate makes use of the same incremental rotation and time delta used in IMU pre-integration to best estimate rotational transformations. As such, linear velocity measurements within the LiDAR frame are linearly interpolated from a buffer of DVL measurements at rate of IMU data capture also within the LiDAR frame to produce a pseudo-sensor measurement containing time, angular velocity, and linear velocity. Determining where IMU data temporally exists within the DVL data queue is made possible by LVI-SAM's fixed lag smoother, which maintains a time lag at key frame rate. This lag time, which is approximately 0.2 seconds for our particular sensor configuration, is sufficient to algorithmically determine DVL measurements that bound IMU data for interpolation.
To validate and support our contributions, we integrate LiDAR, camera, IMU, and DVL sensors on a USV platform within the Virtual Robot X simulator, VRX. VRX simulates the dynamics encountered by USVs operating in complex marine environments with wave, current, and atmospheric forces perturbing robot motion. Sensors have been modeled to reflect real-world performance expected of affordable, commercially available devices. Details on sensor intrinsic and extrinsic calibration will be provided in our final report. 2 riverine environments have been established in simulation. The first environment contains built infrastructure with gray brick walls and a concrete bridge offering complex texture and structure. The second environment is deprived of texture and structure, with opaque white walls bounding the USV to elicit degeneracy in camera and LiDAR. In the second environment, improvements to robustness made by DVL fusion will be rigorously tested given that LVI-SAM currently fails within this environment. By relying on high accuracy, low drift odometry expected from our DVL factor, we hypothesize that our novel DVL factor will prevent failure. We are currently working through implementation bugs with our DVL factor, though expect to see recovery of state estimation in our final report. To assess accuracy improvements made by DVL fusion, we have established a workflow for evaluating relative and root mean squared translational and rotational error. Error is evaluated on the globally optimized loop-closed robot trajectory output by LVI-SAM with and without DVL fusion and compared to the ground truth trajectory of the robot recorded by the simulator. With DVL fusion, we hypothesize a decrease in translational error for environment 1, while rotational error should remain identical given no rotation residual is provided by the DVL factor. Currently, we have metrically evaluated LVI-SAM trajectory without DVL fusion against the ground truth for environment 1 as our base case. In our final paper, LVI-SAM trajectory with DVL fusion will be compared against ground truth, with error metrics benchmarked against the base case. Upon successfully debugging our DVL factor, we expect to conclude noticeable improvement in both accuracy and robustness when the DVL factor is used in tightly coupled LVI-SLAM for USVs. We further expect our method of DVL and IMU reconciliation to become standard practice when implementing our DVL factor. More broadly, we expect that the outcomes of our project will motivate future work in extending tightly coupled LVI-SLAM to additional sensor fusion. Our hope for tightly coupled LVI-SLAM is one where numerous researchers can develop within a common software package, sharing new factors to create a truly accurate and robust SLAM system for any mobile robot.